All right, boys and girls. So today we're learning about the power series. This is the thing that we've been promising since the beginning of class. This idea that you could have two different worlds that look nothing like each other, yet there's this bridge between them. For example, sine of x. Sine of x looks like a trig function. You would never ever think that it's a polynomial. Such as x minus x to the third over 3 factorial plus x to the 5 over 5 factorial, etc., etc., etc. These simply don't look like each other. This one looks like a trig function. This one looks like a long polynomial. Yet, this is the great promise of calculus second semester, that we get to see this bridge. It's famously called Taylor series expansions. And so we are at a really, really nice place in our course because we are ready to explain this once and for all. We already saw a tiny bit of this bridge, and I'll remind you, tiny little example. For example, if I told you 1 plus x squared plus all the way to x to the infinity, we know that that's a geometric series and it's equal to x to the infinity plus 1 minus 1 all over x minus 1. And if the absolute value of x is less than 1, this part converges. And so we have that if this is true, then 1 over 1 minus x is equal to 1 plus x squared plus x to the third plus x to the fourth. So this was the first instance of the bridge between something that is not a polynomial and an infinitely long polynomial. Under some conditions, of course. There's always some conditions, or usually. And then we did amazing tricks. We substituted things for x. We took the integral on both sides. We were able to expand arctangent. We were able to find a formula for pi. It was an amazing day already. That was your first little taste of this promised bridge. But this idea is it can only get you so far. It's a cute little trick, and we can do variations to get a whole bunch of expansions, but maybe not all of them. There's no way to turn that trick into sine, so that we can take, or at least not an immediate way to do it. Maybe there is, but it's not very common to do that. So we want a more general approach. More general. Last time it was exploitation of geometric series and some variations, and that was beautiful. But today we want a much more general, much more powerful approach. Okay, that's why today is such an important day. You're going to get to see unthinkable things. Here, for example, this you could program your calculator to do. This, not so easy, but once you learn how to do it, you see what's going on inside the calculator, whoever programmed it. They wrote some polynomial like this. All this is multiplication and addition. That's why it's so powerful. And there's a lot of other applications, but we'll get to that. Anyways, the way to do this expansion is to try to think about functions differently. Stop thinking about functions the regular way, or try to think about them in a new way. Let me try to explain what I mean. And that's related to, it reminds me so much of just finding the DNA for any kind of creature. All creatures around here have some sort of DNA sequence which is unique to them and makes them who they are. And so it defines the being or the organism. Same thing for functions. I think there's so much similarity. The way we gotta think about it is if some of these functions are polynomials. Let's study polynomials for a second. Polynomials are always made up of powers of x and coefficients. So for example, if I have 1 plus 3x plus 5x squared plus negative 4x to the third plus 7x to the fourth. This is a polynomial, some random polynomial. But what I want to point out is that if I chose a different polynomial, for example, 0 plus negative 2x plus 7x squared plus 11x to the third and so on and so forth, this is a different polynomial. But there are some similarities. They all have x. They all have some sort of x squared, x to the third, x to the fourth. Even if that one is a 0, you could put a 0 as a placeholder, but they all have some sort of coefficient in all whole number powers of x. And so you could extrapolate from that, what is the essence of a polynomial? You could think about it this way. The essence of a polynomial goes like this. It's something plus something times x plus something times x squared plus something times x to the third, and so on and so forth. So in essence, you could think about the polynomial as this sequence. If I have 1 here, -2, 3, 4, this is all that matters. This is the only thing that distinguishes one polynomial from the other. And so this could be, you could think about it as sort of a DNA sequence, but for the function. If every one of these functions is a polynomial, and every polynomial looks like this, and every polynomial is completely defined by the coefficients, then every function at the core of it, the DNA is just these coefficients. If you can get these coefficients, you can get the polynomial just by adding the different powers of x, and then you can get the function. And so you could say, okay, this sequence is 1, -2, 3, 4, etc., etc., etc. This is the sequence that defines this polynomial, and in turn, it defines some sort of function. Okay, that is the connection. That is why I think about a good, powerful way to think about these functions as, think about them as organisms that have very unique DNA sequence. And a DNA sequence is just a sequence of coefficients. Clearly, you want to keep them in order. The first one is for the 0th power, the second one is for the first power, the third one is for the second power, and so on and so forth. So this is an ordered sequence, as all sequences are. Okay, that's the connection. That's what makes a function different. So if I have sine, maybe sine has this sequence, and if I wanted to write cosine of x, maybe it has a different sequence, and so on and so forth. The square root of 1 plus 1 over x, any kind of strange thing like this. They will all have their own different type of sequence. Okay, that's amazing. I love that. So with that being said, the only thing left to do then is, okay, here are some examples. You take some weird looking function that doesn't even look anything like a polynomial, and boom, you derive from it your sequence. And from the sequence, you can get the polynomial. See the 0 and the 0, that would give you 0 constants, 0x to the first, 1x to the 2, a half x to the third, a third x to the fourth, and so on and so forth. So this polynomial is for, sometimes you have restrictions on the x values. They may not work for all x's, as we saw at the beginning for the restriction on the geometric series where we required that the absolute value of x is less than 1. Many of these have restrictions. For example, I doubt that might or might not work if x is -1, then you have trouble because the bottom will be 0. So a lot of these, it's okay to accept that some of these may have some limitations, some restrictions, but where they work, this expansion is incredible. Okay. Here's the famous geometric one. That sequence would be 1, 1, 1, 1, because all these coefficients are 1, 1, 1, 1, 1, 1. I wanted to point out that I'm going to show you how to calculate it, but sometimes the calculation, after you do it 10 or 20 times, it gets a little boring. So sometimes you might want to solicit the help from some sort of computer program. And so I clicked the link here. I think this is a link. No, I guess I have to put it on there. I'm trying to click on this thing. All right. If you download this PowerPoint from the lectures, that should be a live link, and it'll take you to some software that can help you check the coefficients. Okay, the only thing left to explain is how do we get this amazing sequence? For example, for sine, if I could show you how to do it in the general sense, then it would be a really, really good day today. So the way to do it is, I'll show you 3 different ways philosophically. We pick a nice function, right, and pick a point. And the way we construct the function is we first require that the value of the function and the constant are the same. Okay. And then we find the best fitting line at that point. And once we find the best fitting line, that would be a degree 1 polynomial. Keep in mind that this would be a degree 0 polynomial. The best fitting line would be a degree 1 polynomial. And we find the best fitting degree 1 polynomial. And then here we find the best degree 2 polynomial, and so on and so forth. The best degree 3 polynomial. And in this process, in a very methodical way, we are constructing the function out of pure polynomials. And you may think, whoa, that's crazy. But it's not so crazy. You've already done it before. Let me show you an example. You already done specifically this one. I know for a fact if you took first semester calculus, let me give you an example. Suppose I have f of x is equal to x minus 1 squared plus 2. All right. So that would be a parabola shifted to the right 1 and up 2. So I'm guessing it would be some sort of parabola, something like this. And back in Calc 1, first semester calculus, your teacher might have asked you, find the equation of the best, well, actually the way they would have ordered it is find the equation of the tangent line at, for example, x equals 2. We want the equation of the tangent line. So this would be the tangent line. You already know the slope of it. The slope of it would be the derivative at 2. And you know a point on it. A point would be 2 comma f of 2. So using these two things, a point and a slope, any old child can do this. If they've taken an algebra class in middle school, they know that it's y minus f of 2 is equal to the slope times x minus 2. Or said differently, the tangent line would be equal to f of 2 plus f prime of 2 times x minus 2. So you've already done this before. This is the best fitting line. That's the part that you did before in Calc 1. Now, what we're asking for here is don't stop here at degree 1. Have the guts to go on and find the best degree 2. So the question would be, what is the best fitting parabola there? And it turns out that the best fitting parabola may be itself, because in this case it's a parabola, but suppose it wasn't, suppose it was some other weird function. You could ask for the best fitting parabola and it might match it a lot better than the best fitting line, and so on and so forth. That's the principle. And incidentally, here's a little homework exercise for you. Can you stop the video here and use common sense and use all your noodles to do this? Find the best fitting degree 2 polynomial here. If for a general function, how would you do that? If you were good enough to find the best fitting line, in fact, that's just a couple lines of thinking, how would you find the best fitting parabola? And then the best fitting degree 3 and so on and so forth. That's exactly what we're going to do today. So that's a tiny bit of philosophical idea behind how to convert functions into polynomials. Visually, let's do it visually. This would be the best. This is a famous one. This is a sine function. This would be the best fitting line here. If I zoom in here, at this point, the idea is that the closer I zoom in, the more indistinguishable the tangent line becomes to the graph. Again, this is from Calc 1. This is the equation of the tangent line. And once you do that, what would be the best fitting parabola? Well, then this would be the best fitting parabola. Of course, it goes all the way down because it's not sine, but that would be the best fitting parabola at this point. And the idea would be that the closer you zoom in, the more indistinguishable these two become. The further you get, of course, the gap becomes greater and greater and greater. And that's okay. Of course, after you found the best fitting parabola, you want the best fitting degree 3, the best fitting degree 4, and so on and so forth. And in this process, the polynomial version of it gets closer and closer and closer and closer to the actual function. It's like a miracle. It's like amazing to think about it that way. The more polynomials that you approximate it with, the closer these polynomials approach the actual function. And eventually, if you go all the way to infinity, this one will take the exact shape of the polynomial of the sine. Incredible. And that will give you the link between sine and a polynomial of infinite degree, of course. Okay, that's visually, that's philosophically. We asked that it matches. We find the best. Philosophically, we find the best degree 1, the best degree 2, the best degree 3. That's philosophically. Visually, you're making the graphs match better and better and better using only polynomials. This is degree 1 polynomial, this is degree 2 polynomial, etc. Finally, let's do it algebraically. this is where we can actually figure it out. So I told you that all polynomials have this structure. They have a constant, then they have a plus, then they have a constant times x, then they have a constant times x squared, and so on and so forth. This is the structure of all polynomials. Now, talk is cheap. Let's do it. This is the moment. Can we figure out what a naught is? And let's actually put a factual function here, like sine. Let's say that this is our function, sine of x. Okay. So I'm taking sine of x, and I'm going to force it to be a naught plus a1 of x plus a2 x squared plus a3 x to the third, and so forth, so on and so forth. This is a little bit of reverse engineering, or wishful thinking. I'm already wishing or hoping that there was such a polynomial that's equal to sine. Nobody ever said there was such a thing, but here I am arrogantly declaring that sine is equal to some polynomial. We don't even know if it could be true or not. There's a lot more details to be resolved, but let's be hopeful and try to see if we could do reverse engineering under the optimistic idea that such a thing could exist, such a beast could exist. If that was the true, so I'll put a big old if such a thing was true, then when x is equal to 0, we get that sine of 0 is equal to a naught plus a1 times 0 plus a2 times 0 squared plus a3 times 0 to the third plus a4 times 0 to the fourth, and on and on and on and on. But wait a minute, this becomes a 0, this becomes 0, this becomes 0, this becomes 0. So, and I know sine of 0 is equal to 0. So this tells me that a naught is equal to 0. Boom! I already found out the first clue. The first little piece of the DNA for the polynomial. This guy is equal to 0. How amazing was that? Did you like it? Okay, now that was okay, and we found one of the items. We just have infinite many more to go. So don't lose hope. Let's try and see if we can find the second one. To find the second one, I'm going to take a super brilliant idea and kill this one. The super brilliant idea is to think, what would kill a constant? The thing that would kill a constant is if I take derivative of both sides. Take the derivative of that and take the derivative of that. That would make that constant disappear, and it would look like this. So here we go. From here, I'm going to take the derivative, and I'm going to go here to the bottom line. This will tell me, what's the derivative of sine, by the way? It's cosine of x, and that's equal to a1. That's because I'm taking the derivative of this. The derivative of the constant is 0. The derivative of this is just a1. The derivative of this would be 2 times a2 times x. So it would be 2 times a2 times x plus 3 times a3 times x squared plus 4 times a4 times x to the third plus, what else? 5 times a5 times x to the fourth, and so on and so forth. And now, if x is equal to 0, what does that tell me? That tells me that cosine of 0, that's 1, is equal to a1 plus, oh, here we go. This guy's going to go to 0 because I'm going to plug in 0 here. This one's going to go to 0 because 0 squared is going to be 0 times that is going to be 0. This is going to be 0. In fact, all this is going to be 0. Anything that has an x, if I'm plugging in x equals 0, will vanish. And so all I have is a bunch of zeros here. And I get the amazing conclusion that a1 is equal to 1. And whoa, I figured out two pieces of the DNA. I know that the first one is equal to 0, and I know that the next one is equal to 1. How about that? I love it. So we got 2 down. We only have infinite many more to go. It's like that song, 100 bottles of beer on the wall, 100 bottles of beer. You take one down, you pass it around, 99 bottles of beer on the wall. In this case, you take one down and there's infinite many more constants to go. And you take one down and there's infinite more constants to go. Fun, right? Okay, so we only have infinite many more to go. We got that one, we got that one. Okay, how do we figure out A2? Okay, I'm going to take a pause here and then come back. Okay, sorry, don't worry.